for C33. And in fact, in general, you'll see the code here. And this is the YouTube channel here. So if you are looking for like the video for this week, it will be on this channel. And Ken actually made a note that if any of you don't have access to YouTube, then let us know and we'll figure out something else. That means that like we'll have another platform where we post this stuff in addition to YouTube. Yeah. So some people had a question as to why they got 0 for assignment 2. Actually, maybe I'll just talk about quickly some logistical issues before we start this tutorial. So let me start. So there were some logistics people had questions about. So for instance, some people were wondering why they had a 0 in assignment 2. You don't have a 0, it's just that the Quarkus interface for quizzes, it kind of makes it so that, you know, it says 0 until I update it. That's because, you know, technically speaking, unless you directly hand it to the actual quiz interface, it will assume you had no submission. So when it times out, it will assume you didn't submit anything, even though you did. So you didn't get a 0. It's just I have to override it with your actual grade manually when I mark it. So yeah, you didn't get a 0 if you submitted it, you know, on time, and don't worry about that. Hopefully the assignment 1 marks will be up soon, right? So yeah, that's the logistics issues. If anyone has any questions about that. Oh, so here. So this is somebody called it no title in the discussion board. So it's in the, we put it here. Yeah, so I'm just gonna post it here. I'll just, you know, like maybe I'll just copy the link. So let me open this link and I'll just you know, so oh, that was my last week. So here's my page. So I'm going to post it here. Yeah, so here you go. Oh, I sent it to Christina. I'm sorry, guys. Okay. So you guys know, right, that today you're going to be discussing, or your tutorial for this week is going to be effect size, right? So effect size, sample size, your alpha level as it pertains to power. And we're also going to be discussing sign tasks. So anyone know, and this is, both of these things are related in the sense that like, it's something we're curious about in the context of estimating where a parameter happens to truly sit. And the question is, when is the best test to use? How do we actually get the best test given our data? And these are the features of this tutorial, right? Does anyone know what power is by definition? So power is what? It's a complement of what? So power is a complement of the type 2 error. I mean, the type 2 error is, yeah, where beta is a type 2 error. So Jackie's saying it's 1 minus beta, and beta is actually type 2 error. So this is the probability that you did not reject the null hypothesis when you should have. So this means the alternative is actually true, and you did not reject it. You did not reject the null hypothesis. So of course we don't want this to happen too often, right? Because you can imagine in a lot of scientific studies, you really want to see an effect in some sense, right? And so if you actually yield a situation where the probability of actually seeing said effect is very low, your test is not very good, or maybe you really don't have an effect, either or. But there are 4 quantities that really actually in some sense influence this relationship, right, between this, you know, there are 4 things that have a relationship with power, and that is the sample size, the effect size, and the significance level. Error that we should have rejected the null hypothesis. So Kim, it is the error that you should reject the null hypothesis, but your alternative is actually true, but you did not actually accept it. So to put this into context, imagine you're in a court, right? And the court of law says the default is innocent until proven guilty. That is your alpha. Your alpha is like innocent, and you don't want to make the mistake too often. So given that the person is innocent, you actually convicted them. That is actually your alpha. If the person's innocent, you convicted them, this is alpha. In contrast, beta is the person was guilty, but you said they were innocent, basically. Right? So you failed to reject the null hypothesis. You failed to see that they were not innocent, and you said that they were, basically. Right? So we are always trying to mitigate those two things. We don't want either of those two things to happen too often. And so the thing that actually influences those things are the sample size, the effect size. And so power is also influenced ironically by significance level. And significance level for us is actually considered alpha, right? So this is actually alpha. So let's say this is alpha, right? So it turns out that when your power is actually inversely, or so your alpha is actually inversely related to your type 2 probability, which we'll talk about later on. And this means that when your alpha level is actually going down, your power actually decreases as well. So we're trying to actually keep these things in mind when we contextualize how to get a best test for our data, right? So, and power obviously is going to be the complement of the type 2 error, which means that if your type 2 error is too large, your power is low, you don't have a very good test, right? So these are the four things we're going to look at within the scope of power today. So let's go back to our empty cars example. Remember, we did a test last week and we said that we're looking to see if our weight of the cars is different from 2. So I knew it was 3.2 because I looked at the mean, right? So you should never do that, obviously, in data analysis. You shouldn't peek at your data. But I knew that the true mean was 3.21. And so that's why I did a test as to whether or not the mean is different from 2. Right? So I wanted to know, is the mean different from 2, knowing that it actually was since I peeked, right? And these were all the criterions. My alpha level is 0.05 because that tends to be the default you see in a lot of sciences, right? Your sample size was 32. Because if I just have a look and see, so just to convince you guys there's 32, if I look at the length of, let's say weight, it's 32, right? So this means that our quantile is going to be a function of your alpha, your quantile level, which is going to be 1 minus alpha over 2, so the 97.5 percentile, as well as the sample size. So we know the degrees of freedom is n minus 1. So our criteria quantile is actually 2.03. And then we're going to perform we ran a t-test. We wanted to know, right, what was the probability of actually reducing the null hypothesis given the evidence we saw, right? So we saw this evidence and noticed that, well, quite frankly, the t-value is very far from 2.0. So you can see this is reflected in the p-value, which is very small. This is a two-sided test because it says not equal to 2. But you can see that we actually have a decently big enough effect size. So even with the sample size of 32, which isn't huge, right? We can see that we're far from actually 2. In fact, we know the mean is 3.2, so that intuitively makes sense. This is a correct rejection. We saw, well, in the context of like, let's suppose we truly knew our mean was 3, it would be a correct rejection. Although we don't actually know because this weight of cars is only one realization of the weight of cars. It could actually be the case that when we take another weight of cars, it could actually give you a different test. But if we truly knew our weight was 3 and we saw an effect that said different from 2, then we would correctly reject. And in fact, we're gonna actually look at that. Let's put this example in a better framework. And by that I mean, like, let's actually pretend that we can sample from a distribution that we know is actually normal, right? Because we looked at this one last week and we knew it wasn't quite normal. So let's actually improve our test a bit in the sense that, like, I don't truly know that the weight of these cars at the population level is actually 3.2. All I know is at the sample level is 3.2. So there's always a chance that our test is wrong, right? But in this context here, I'm going to sample from data I know is actually truly normal. And this way, I'm going to yield, right, something that I know for sure is actually whether the test is correct or not, right? So first of all, I'm going to say that I kind of made some new code for you guys. So if any of you are doing assignments and you want to use the LaTeX, you can see that this is LaTeX. So, this is actually, whenever you put a $sign, it gives you the math mode. So this is what you actually see. And in fact, I can run this and you're going to see that it will create a really nice PDF in LaTeX. All right, so let me show you guys this. There you go. So notice that when I look at my document, what I actually see is this very beautiful PDF, right? So yoink, let's go in and we see this. This is my test, right? I want to know if the mean is different from 2. Now, full disclaimer here, you can actually see that I know I'm sampling from a distribution that is not mean 2. So I know for a fact the true mean is 3 because I sampled in that way, basically. Right, so I'm sampling with a distribution that is truly actually not mean 2. Right, so first of all, I'm going to set the seed. If I don't set the seed, then it's going to give me a different permutation of my observations each time. Right, so I'm forcing it to give me, right, 10 observations that are going to look the same each time because I've set the seed at 1. Or you can set the seed to whatever you want. You can even put your student number and it'll give you a different permutation, but it will fix it. Right, so I'm going to point out that this is not the default for R norm. The default for R norm, so if I go to help, R norm, you're going to see that the default is actually mean 0, variance 1, standard deviation 1, because we're always fixated on the normal, the standard normal. So the default is obviously going to be standard normal, basically, right? But you could change it. And in fact, I did, right? So if you don't specify a mean and a variance, and a standard deviation, sorry, it will assume that you're actually meaning you're taking 0 and 1, right? So for instance, if I do something like R norm of, let's say, 100, it will give me 100 different observations, but you can see that what it's doing is it's assuming that the mean is 0 and the variance is 1 because I didn't specify anything different, basically, right? You also have a D norm, so this is the density. If you want to work with the density, here's the P norm, which is a CDF, the Q norm, and then here's the R norm. Right? So this is all of those things. Yeah. So let's actually sample from something that has a mean of 3 and a standard deviation of 1, and that is a sample of 10. So then I'm going to do the same test. So given that, I'm going to say that is my actual thing different from 2? Now I know for a fact that the true mean is 3, and the question is how often does my actual data show that truth, basically, right? There's a chance it will say something the opposite to what's the truth a certain amount of time, basically. All right, so this is my data, and right, so this is the data here, and then here's the test. So what you actually have is that at the P level, I have a 0.01315. So it's going to lead to a correct rejection of the null hypothesis when it's actually false. We know it's false because we sampled in that way, right? But obviously there's a proportion. Now, what is the P value? It is the probability of actually, right, incorrectly, right, rejecting the null hypothesis when it's actually true, right? So there's always a chance, well, in this case, we know it's not true, but there's always a chance that your test yields the wrong conclusion basis. So we need to know how often this can happen given our data and our sample size, because it's always going to be a function of your sample size, your effect size, etc. Those things work at play to determine how often you make an incorrect mistake, basically, right? So now, in his lecture, he has a function where he runs this numerous times. So this means that in order to obtain the p-value, or even to obtain the power, basically, to obtain the power, what is the power? It is a proportion of the times that you reject the null hypothesis, basically. Literally, the power is how often you reject the null. So we can actually put a test on this. And what Ken does in his lecture is he actually simulates 1,000 times this t-test to determine how often you're going to reject a null hypothesis. Now, remember I said that this power is related to your p-value. So this function is going to actually give me a power that is in some sense related to how low I specify my actual alpha, basically. Now let's see how this is working. This is the actual function he posted in his lectures, although I'm changing things to match the test I'm interested in. But you have to download tidyverse because you have a bunch of functions, like these map functions exist in the tidyverse space. But map is going to actually run the simulation 1,000 times, right? Given this variable of 100, 3, 1, it will run this test, right, 1,000 times, and I can actually probably set the seed. So if I set seed and just say, let's say 21 or something, it's going to actually run this test 1,000 times, right? And then it's going to put these outcomes into this t-test. So it's going to take, every time it runs through the loop, it will take the test and compare it to a mu of 2. Then it's going to, the map on a sort of DBL is saying, well, we recognize the p-value as a numerical value. So let's use the function map underscore DBL to pull out that p-value. You can actually use map character like CHR, but not in this context. If you have characters you're using pulling out from your data frame, you can actually pull out characters using map underscore CHR. So the actual map function you use matters for context of your actual data frame. Basically, you have to be careful in this way, right? Now, end frame is going to actually pull out those p-values and put them in context with, right, a data frame. It's going to create a data frame of all these p-values. Why am I doing this? Because I want to count how many times my particular p-value is less than 0.05, because when my p-value is less than 0.05, I'm going to reject the null hypothesis, right? So this rejection means I'm going to actually conclude the alternative. So you can see intuitively that if I set my p-value to be lower, I'm then going to have a lower chance of actually, rejecting the null hypothesis, basically. So in that way, my power is going to actually go down. So when you set a p-value, it will actually, in some sense, dictate how often you accept the alternative, because there's an obvious relationship there. Basically, when the p-value is lower, the test becomes more conservative. So let's run it and see what we get. So when I first ran the test and I did not set the seed, I got this p-value of 798. So that means that instead of having a true of 809, I actually had a true of 798, right? So now my true is actually 809. So I can change this. And notice now that whenever I run this seed, it's gonna hold, right? So it's gonna hold at 809 every time because I've set the seed at 21. Please be mindful of this, right? When you run your assignment, basically, and if you do your analysis, and you realize you made a mistake, right? And you want to go back and change your error, and you try to rerun your code again, but you didn't set the seed, everything changes. You have to redo all your analysis. So make sure you set the seed to avoid having to redo your analysis again, because you got new outcomes basis. This is something to keep in mind, basically, right? So just for your own buyers beware kind of thing. Yeah. So this means that my power now is actually going to be 0.809. So it's about 81% basically. All right, so this is actually his simulations we've done, but notice that there's a built-in power function in R that's doing the same thing. It's actually also going to perform the simulations a number of times. It's going to give you a different p-value each time, and it's also assessing the portion of times in which your p-value is less than your actual alpha level. Right, so now let's do the power task. So I'm going to take a sample of size n that's 10 to match what I have here. And I'm going to take my delta to be the same as the one I had above, which is going to be, so the delta is actually going to be 1 as well, because you see your actual mean is 3. You're testing a level of like your mu is 2. So the delta is the same as what you see here. It's the same delta. And the standard deviation is 1. So now this is a one sample test. I'm hypothesizing if you run it once and it's type 2 error, if you run it once, so if you run the power test once, like this test here, or are you referring to the test up here? So if you run this test once, you don't actually have a power. You can't compute power, because the whole point of the p-value is supposed to be the p-value and the beta. So the alpha and beta are supposed to be in some sense contextualized with the context that you sampled many different samples of size n. So once you sampled many samples of size n, a certain proportion of the time you failed to reject the null hypothesis, and a certain proportion of time you rejected it basically. So when you only have one realization of this task, in theory, your alpha and beta are not really conceptual concepts. You can't look at one fixed sample and run a task. So we're actually thinking about like multiple samples of size n where we ran this test, and sometimes we may be off, right? And if you can think about it, it's almost like when you look at a confidence interval, it's the same game basically, where let's suppose your truth theta is here. Sometimes you got a confidence interval that did this basically, so it contained actually theta. Sometimes it was here, so it didn't contain theta. But maybe it was here and it contained theta, it didn't contain theta, contained it. Then this means you ran actually this many samples of size n, right? So you actually sampled this many times. So 1, 2, 3, 4, 5, 6, 7. So this is 7, I suppose, right? So I should probably sample more, but let's do it again. So sample again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this means that 2 out of 10 times my actual interval did not contain theta, which means my actual alpha here is like 0.2, which is pretty high basically. All right, so what it's saying is that you have to sample more than once to even conceptualize or think about this notion of an alpha or beta. If you only sample once, you can't really talk about this notion of type 2 error, type 1 error, because it's referring to the error you get when you sampled many different fixed samples of size n, basically. Right? Is this clear for you? So this means, so the n you choose. So usually the reason we chose 1,000 is because it's nice to compute it. You can see that I can directly compute the actual power, because 1,000 something, it's like related to 100%, right? Easily, so we can directly compute the power. Sometimes the numbers, sometimes we like to do 1,000 simulations. It's just something that we see a lot in statistics. Like 1,000 is a big enough number of simulations to feel confident. Because remember, probability, at least in the frequentist approach, right, is a long numbers game. Like you have a lot of sequence of events. It's a long sequence of events, basically. It's probability. So you have to actually do the trial a long number of times, basically. So you want to simulate enough times to actually see the true phenomenon that you should see in nature. So when you sample a lot, many times a different sample of size n, then you get a true idea what your actual parameters look like, or what your estimates look like, right? When you only sample a couple of times, you don't really have a notion as to, because you don't have a long sequence of events, you don't have a working concept as to where your actual things are falling, basically. But when you do it a lot, you tend to get a stability in your estimates, so you feel more confident. That's why we like to do 1,000 times, basically. But this n you're referring to is not the actual sample size, it is a number of simulations, right? So keep this in mind. So there's an n that's relating to the number of simulations, and there's an n that's your sample size. You notice that in this framework here, there's actually n, the sample size is n, but my simulation's 1,000, so they're not to be confused. Just be careful of that. So here I'm going to do a PowerTask with a sample of size 10, but intuitively it's doing the same thing as a simulation here. It's taking many samples of size 10 and performing the test space and seeing how many times your p-value is less than your alpha of 0.05. So if we run this, we get this test here. Notice the power you see here is actually pretty close to what we obtained here, right? The power is pretty comparable, right? So that makes sense, because this power is in some sense certainly related to your sample size, your delta, and your alpha level, basically. So because I set the alpha level to be similar to my simulation, it's doing the same thing as my simulation. So because it's a built-in function, it's doing the same thing. That's why I'm not surprised by the outcome I got, basically. Right, but now let's manipulate things. Let's actually change our sample size and see what happens. And let's change our alpha level. Let's change, the effect size and see how this influences our power. Right, so does anyone know what should happen to our power if we actually increase our sample size? Anyone have any guesses? Exactly, so the power goes up. You might say, why on earth should the power go up? And the thing I talked about in the last class was a lot of the times your estimator becomes more consistent when you actually increase your sample size. And to understand why that's the case, we can actually have a look at what happens if we just actually literally sample our norm. Let's say a sample of size 5. We know the mean is 3 and the variance is 1. So we're taking a random variable and we have a small sample size of 5. And let's see what happens. The histogram looks almost uniform. It kind of doesn't even look like anything that's normal, basically, right? So now let's see what happens if I increase my thing to 100. It looks more symmetric. And let's see what happens if I increase it to 1,000. It really actually gets tight, basically, around 3. Now, this is not an accident, right? So we know the center limit theorem tells us that if we actually increase our sample size, we actually push our actual sample towards a true population mean base by a factor of root n. Right, so we're pushing our sample towards the actual population mean by a rate of root n, right? And so intuitively, it makes sense that we actually get a standard error around our estimate that is tighter. It's because when you increase your sample size, you know that sigma over root n, which is your standard error, gets smaller basically by a factor of root n, basically, right? So you increase your n, sigma over root n is getting smaller and smaller and smaller. You see, of course, in some sense, your actual standard error decreases. You're going to actually see a better estimate around your actual, again, a better point estimate for your mean, basically. And this way, you're going to actually see effect sizes much more clearly than you would have if your sample size was small. Right. So now let's actually put to the test what we already know to be true and just see what happens to our power. So this is a vector I've created with 5 different sample sizes, and I'm going to use a power test. So I'm going to keep all the things the same as before, except now I'm going to feed in a sample size of given as this vector. So it's going to compute the power task 4 times, right? And it's going to extract the power. So it's going to, this dollar sign of power is because my power function, I call my power function PWR, so I've called it power. And I'm going to pull out the power estimate from the power function basically for each of the times I run the actual power function. So let's see what happens when we do it. So notice that this is what I get, right? And so we knew intuitively that our power should go up as we increase our sample size. And in fact, the power is at an all-time low when you have a sample of 5. When we simulated it, it didn't even look normal. We had a very poor crude estimate, and we had a very wide standard error because the sample variance on the actual estimate is very big, and the sample size itself is small. So we look at the ratio of sigma over of S over root n. So when you look at S over root n, in fact, it's big, right? Sorry, so when you have S over root n, it's very big. It obscures your t statistic base. This is why you fail to reject null hypothesis, right? So again, when your sample estimate is very big, as it would be with such a very, your standard error is very big as it would be when you have a very small sample size, because S over root n is very big. Since your sample size is small, when you look at the ratio of your t statistic, where you have your actual difference, which is your effect size over the actual standard error, it's small because your standard error is too big, right? So this is why you don't really see the effect you should see, and you're less likely to actually reject the null hypothesis, which is what we expect. But when you increase the sample size, you essentially shrink your standard error because the root n factor is getting bigger in the ratio of sigma over in the ratio of S over root n, and so ironically, your actual t statistic is getting bigger because the ratio of S over root n is smaller, and when you divide it over the same effect size, the t statistic blows up basically. Right? So when you keep making your precision tighter and tighter and tighter because your sample size is getting wider, your t statistic gets bigger, it blows up basically, and you are more likely to reject the null hypothesis basically, which is what you're seeing here. Right? So again, you blow up your actual t statistic because your actual S over root n, your t statistic ratio is getting smaller. And you blow up the t statistics. So you're going to have a p-value that's obviously going to be very, very small. It's going to be smaller than your 0.05 level. I just want to point out here that I did not actually specify an alpha level. That's because the built-in alpha level is 0.05, which is what I put here. And so keep in mind that you can specify your own alpha if you don't want to take 0.05, which I'm going to actually do in a bit. And the default is given to a 0.05. And this is obviously, yeah, so you give it a sample size, the delta, an S, and a type 1. This is a type, so you can also do a two-sided test here. Oh, not a two-sided test. You can do a two-sample test. For me, I'm doing like a one-sample test, but you can also look at the effect size for a difference of 2 different independent groups if you wanted to, and then you just change the type to 2-sample. I just want to point out that this delta is 3 minus 2 because my actual, the true mean, what I saw in the sample was obviously 3, right? But what I think is, what I hypothesize is 2 basically. So this is why it's 3 minus 2, right? So what happens if I actually change my alpha? So this is what we should think a bit about, basically, right? So, just think about this. This is the one that people have the most problems with. It's always intuitively obvious people that, like, when you increase your sample size, you of course, increase your power. But whenever I say when you decrease your actual alpha, you decrease your power, people pause and they say, why should that be the case, right? So does anyone know why your alpha level actually, if you decrease your alpha, you decrease your power? Does anyone have any ideas?
Isn't it because you're allowing a higher chance of a type 1 error to occur?
Or you're allowing for a lower chance of type 1 error?
Oh, sorry, yeah.
By that I mean, so I think what he was getting at, right, is that, like, when you actually make your alpha level smaller, alpha is a probability of making a type 1 error. So you're less likely to reject the null hypothesis, right, when you actually make your alpha smaller. So you're then asking for even more evidence to debunk the null hypothesis. But asking for more evidence means that your test becomes even more conservative. So you're actually less likely to reject the null hypothesis because now now the actual alpha level you're asking for is way in the tails. You're literally asking for an alpha somewhere far in the tails, and this is getting more and more difficult to actually adhere to, basically. And so you can actually notice that when you decrease your alpha level, so when you make it so conservative, you actually increase your type 2 error. So type 2 error, remember, is in the court of law when somebody is actually guilty, but you said they were innocent. So when you truly have an effect, but you rejected the null, you failed to reject the null hypothesis, you essentially ignore your true effect you actually have. This is actually increasing your alpha level is getting smaller, because if you're less likely to actually reject the null hypothesis, that means you're actually less likely to accept the alternative, basically, right? So your type 2 error will go up. You're going to ignore the effect you actually truly have because you're not willing to actually debunk the null hypothesis. And so this means that if your power is the complement of your type 2 error, of course, if your type 2 error is increasing, as in you're less likely to actually accept the alternative, then you're certainly going to actually increase you're going to decrease your power, basically, right? So your power decreases as a consequence of your increasing like type 2 error, right? So this is what I put here, that in fact, 1 minus the probability of type 2 error is equal to power. So of course, if you make it more difficult to reject the null hypothesis, then certainly you're not going to accept the alternative when it's truly actually true, which means this probability of type 2 error will increase. So of course your power decreases. And let's actually put this test. Let's put this working theory to the test, right? So let's actually manipulate our alpha level, right? So instead of looking at like a default of 0.05, now let's introduce a new level into our power function, right? So I'm going to take the lowest power to be 0.01 and the highest be 0.1. And then now, instead of assuming the defaults, remember, in the previous one, I didn't have to actually specify an alpha because the default is 0.05. But now if I want to actually specify an alpha, I have to state it. So now I'm using this notion, I'm using this thing here that says sig.level is equal to alpha. And I'm putting these 4 different levels into my vector, right? So I'm going to then get 4 different powers that are a function of how the alpha level is changing, right? Because if you remember this test up here, what we were actually doing is comparing the p-value we obtained to the alpha level here. So instead of actually having a default of 0.05, now you're going to have 0.001, right? And 0.05, 0.1. And you can imagine that when your alpha is when this alpha is getting smaller, the proportion of times you see true is itself also getting smaller. So you're not going to see your p-value is less than 0.001 too often. So this true proportion will invert, right? So now you'll have more falses than trues because your p-value, your alpha level is just too low, basically. Right? So because remember the power test is doing this basically, it's comparing this p-value to your alpha level. And so when you drop your alpha, of course, you're going to make your table look different. You're going to have more falses than trues, and now suddenly you're going to see your power is going to decrease because your type 2 error is going to increase, right? So let's see what happens in this framework, right? So if we do this, we actually yield this. And so as we expected, the power is really bad because what you're actually saying here is the probability of making a type 2 error is like 85% because it's the complement of power. As in, like, you're almost never going to actually accept the alternative, basically. So you're almost always going to fail to reject the null hypothesis. So your type 2 error is going to increase in that way, right? So if you always accept the null, quote unquote, I should never really say it, but if you fail to reject the null, you're going to obviously dismiss the alternative more often than you should, basically. And so obviously, this is why we don't really use an alpha level this low. It's too conservative. We also don't really use an alpha this high because you can see that what you're saying is that your actual 90% of the time you're going to actually accept the alternative. That's too high, basically, right? So we almost never use something that's low or something that's high because it looks contrived, basically, right? So this is actually also too high. What you're saying is you're almost always going to accept the alternative. This is why we tend to stick to this golden standard here. You tend to see a power of 80% with an alpha of 0.05 because in a lot of literature and a lot of statistical sciences, because it's not as conservative as the first alpha, but it's not as like liberal as the last one either. So the last thing we can look at is the effect size. So now I'm going to change the effect size. So remember that we've been looking at the effect size of 1 the entire time, right? But now we can ask ourselves, well, what happens if I, in some sense, decrease and increase its effect size? So you can imagine that even at smaller sample size. So if I fix a sample of size 10, when I make my effect size so big that it's unanimously obvious that I have an effect, then I'm going to start seeing a very high power, basically, right? So, but when your effect size is very small, like in the tunes of less than 1, and then my sample size is very small too, so that your standard error is very big, you cannot see very small effect sizes with very small sample sizes because the standard error is just too big, right? But here's a fast fact here. Here's a disclaimer here. I'm not saying that we should actually increase our sample size to be 1 million data points in order to get the effect we want, because you could actually, as a statistician, pick up measurement error by accident because you're taking such a big sample size that even when you have measurement error and you truly don't have an effect, you observe it because you're fishing for an effect so small. So for instance, if your difference is like 0.01, which is really not much, but you take 1 million data points, you will see an effect. But is that really actually an effect? Probably not, basically. So we have to be a bit careful not to contrive our evidence, right, by taking huge sample sizes to see what we want, because that's also not good statistics, right? So, but let's see what happens if we manipulate the the effect size. You can see that as your effect size is very small, you get a very poor power because the probability of a type 2 error is too high, right? Because your standard error is too big. And when you keep increasing your effect size, this is the effect size we saw before, so this is 80%. When you increase your effect size, oh, looks like I have 1 twice. I didn't need that. That's funny. When you increase your effect size, you actually see that you have almost 100% chance of seeing, of rejecting the null hypothesis, basically. And I think I actually meant to do 1.5, not 1. I meant to do this. Yeah. There you go. So you can see that as you increase your effect size, the chance of actually seeing a type 1 error, or the chance of actually your power going up to 1 is increasing and increasing. Like, because at some point your effect is so big, and so your actual hypothesized mean is so far off your actual sample mean that of course you're gonna have a power of like 100%, basically. Right, so this is when you hypothesize very poorly, like when you give a hypothesis that really makes no sense, no working sense, you can actually see really strange things happening, like you have a power of like 1 because your evidence is really not even supporting your initial assumption at all, basically. Yeah, so that's the 3 different components. So the effect size, your sample size, and your significance level, those 3 things really actually have a huge influence on your power because of the relationship between alpha and beta. And how they work together to kind of influence when we actually accept the alternative and when we reject it. And so this is something we need to keep in mind. And this is going to be actually one part of your assignment next week. So you can play around these numbers. And that's actually why I gave you guys this for fun thing to do. You can actually change the alpha levels yourself and rerun this analysis with this alpha instead, and then see how you got. With this effect size, see how your effect size changes if you kind of make it really small, right? So this is a really small effect size. Oh, so this is not the p-value, this is the effect size. So when your effect size is really actually very small, you will see that you're almost never going to actually reject the null hypothesis, right? So this is kind of an interesting thing to do for fun. I mean, it substantiates your theories, right? That we have this working theory, and why is it true? We can actually simulate these ideas and find out. But the last topic of your assignment next week is actually the sign test. So I want to point out that we know there's a duality between the t-test and the confidence interval, right? In the sense that, like, when you have data that is normal, right, they tell you the same thing. They give you some kind of idea as to where your parameter happens to be, right? So when you have a symmetric interval, you can then say that given a C% of the time, most of the time 95%, if we sample many times, and this idea here where we sampled many times, we got this different intervals, right? So C% of the time, you actually truly, you're going to see your parameters in that interval, basically. Sometimes it's not in there, as we saw, here and here, where our interval actually missed our true parameter. But we're thinking that, like, if we set an alpha level, that 1 minus alpha% of the time, our interval contains that parameter, which means that if your t-test yields a rejection of the null hypothesis, as in, like, your t statistic is so much bigger than your t critical value that it's in the tails, it's going to be aligned with your confidence interval will not actually yield your hypothesis parameter. It's not going to contain your parameter because your evidence is far from your parameter of interest. So if your evidence is far from your hypothesized parameter, it's not going to contain that in the interval. So that's the duality there. But I just said that this is something you can really use when your data is normal, basically, right? So this is a huge stipulation, right? Because the t-statistic is a ratio of a normal and a chi. So if you don't actually have normal data, you're making an assumption that's not quite right, right? And so I actually said last week that when we use the weight variable, we should have been a little bit suspicious about using the t-test, because if you look at the histogram of the weight variable, it didn't look quite right, right? And what do I mean by that? I mean that when I plot the weight variable from the, we started off this demonstration with, it looks like this, which is not symmetric. To me, it looks honestly uniform, but I can even maybe say it looks somewhat skewed to the left, right? But it's certainly not symmetric. It looks, I mean, actually, generally speaking, a uniform distribution is symmetric. It's a symmetric distribution, but it doesn't have a mode, right? So this is actually kind of not centered around our mean, which we know to be 3.21. So we don't know if necessarily if the t-test is the best test to use in the context of this data. And so we need to think about this. And the thing I'm going to pose to you guys, and you guys can tell me what you think, is like, if we cannot use the mean, and what they tell you in statistics 101 a lot of times is that like you shouldn't use, you shouldn't really use the mean when you have skewed data or data that's not necessarily normal, but you should instead use what? What do we use instead of the mean?
The median?
The median, exactly, right? So we are keen to use the median when we don't have center data that it looks symmetric and normal. Okay, so the question is then, what is an appropriate test, right, for data that is not, that where we can use the median, right? So if you recall, we did actually do the t-test and we got this test, but the question is this really an appropriate test to use? Because we're assuming it's normal, but giving our data, we're not sure, right? So now we said that the median is a good idea to start. So now let's have this framework in our mind, right? So I'm going to peek again, but I'm putting a disclaimer here in the green that peeking is not right, right? So you should not have a hypothesis that you want to work with only after you peek your data. So peeking is not good to formulate hypotheses, but I'm going to do it just for illustrative purposes and show you guys the median is actually 3.325. All right, so why am I doing this? I'm doing this because I want to know, because remember the initial test we had was, is our mean different from 2? So I'm going to use the same idea here. Is our median different from 2, right? Except now I'm going to keep in mind the distribution is not looking symmetric and recognize that and try different tests, basically. Now, obviously, if you sample each observation independently, basically, then whether or not they are or not above the median is a binomial thing, basically, right? So it's either true or it's not, right? So you remember that if you don't sample independently, you have a hypergeometric distribution, right? But if we sample independently, it's binomial. So it either is or is not actually above the median, right? So therefore, and we're doing this with the N trials, basically. So we have this, and of course, you might ask yourself, well, why is P equal to 0.5? Well, P is 0.5 because it's the median, basically. So 50% of the observations are above it, 50 are below it. Now the question is, how likely is it to see very extreme P values? Like how likely it is to see, how likely is it to see, for instance, if your P value, if your median is like 50th percentile, how likely is it, for instance, to see out of 32 observations, 20 is bigger than, let's say, 2. How likely is it to see like 25 is bigger than the median of 2, right? So how many observations are bigger than 2? And does it make sense with the distribution of P equals 0.5, right? So because we know that the median is 50th percentile. So let's put this into context. I'm going to count how many observations are bigger than the median of 2 for the weight of car, for weight car, basically. So I have 28 out of 32 observations that actually have a weight that is bigger than 2. And 2 is the median that I've hypothesized, basically, right? So I'm going to put this into R because I know it's binomial. So first of all, the first thing you feed into the binomial, which is the density, is the number of trials where your thing was bigger than 2, which is 28. then the sample size, which is 32, and then P is equal to 0.5. So it's actually X N P is what you get, right? So, you know, you're just kind of like, so it's D binom, right, of X and P. And does anyone, so is this finished? Am I done here? This isn't complete. Does anyone know why this answer is not finished? What did I actually find here? I found the probability. So what I actually found, basically. So I found the probability that X is equal to 28. But what am I actually looking for, though? Is this what I'm looking for?
I want the probability that X is greater than 28.
I'm looking for bigger than, exactly. I'm looking for bigger than or equal to 28. So what I want is all the observations that are as extreme or more extreme than 20. So if any of you took B57 with me, and I'll always find the p-value is the probability that your observations is extreme or more extreme, right? Bigger given the evidence basis. You're not looking just for that observation alone. You're looking for all the observations that are as extreme or more extreme than, right, what you observe basically. So we're not looking for this. We're looking for this actually, right? So I'm not done yet. Right, so this means that what I'm actually looking for is a table of all the observations of 28, 29, 30, 31, 32, because those are all the observations that are as extreme as 28 or more extreme, basically. And I'm going to actually count up their probabilities, basically. So that's what I'm actually looking at. So what I actually have is this. So when I add it up, I get something that's slightly bigger, which is this. Now, this is actually a one-sided task, right? So you know, let's make a note here. Answer. We will fail. No, we will reject the null process. We reject the null at the alpha. So this is me using LaTeX for those of you who are going to run it. For those of you who are curious for your assignments or whatever, equals 0.05 level, right? But no, this is a one-sided task. As in, like, if I want to actually get the different from, I really have to actually multiply it by 2, basically. But this is true, even if we multiply by 2. But keep in mind, you actually really did one-sided task. Because you only looked at this, but you actually really want, if you want to do two-sided tasks, you actually want, you know, for a two-sided task, we want this times 2, right? So, you know, you actually want this times 2, right? 2 times this, right? So just keep this in mind. Yeah. Is there a way to actually do this without having to brute force it like this every time? Yes. And I'm just curious. I just want to check something just out of curiosity. P binom. I want to see what happens if I do weights. 32, 0.5. I just want to see what happens. Oh, yes. Let me just do 28. Just want to see what happens. Yeah, so 1 minus this. Let me see. Yeah, I just want to point out that I suspect this. So this is the CDF. So PDF is, you know, this is a CDF. So I suspect that P binom is a CDF, basically, right? So just if any of you are curious, how do you, I think you can actually do this as well, right? So P binom is a CDF, which means that it gives you the area up until or equal to. So this is, as in, like, is giving you all the area up until 28. So 1 minus that should be the tail, basically. So that's why it yields an answer that's similar, basically, right? So this is why this looks similar to this. I think it's actually the tail, basically. So you could have done that as well. But anyways, is there a package that you could actually do this? Yes, the Professor Butler, you know, actually made a package called SMMR, so it's a sign test. And I just wanted to point out that people had problems with installation of dev tools. You have to download to use this package first. So you have to download to use this in conjunction to dev tools, right? So, and then afterwards, you should be able to use SMMR, which is in the dev tools package, I think. Right, he has it on his slide. So this is actually on slide page 18 of his lecture for the sign test, basically. So I'm just gonna put that there, right? And I downloaded the package, obviously, so I'm going to run it. And so this is the sign test with weight as 2 and with weight, which is the variable I'm interested in. So I give it, this is sign test as give the data frame, which is empty cars, give the variable you're interested in, and then the weight, which is 2, right? So this is the test. Is the median different from 2? Notice that this is the upper thing we're looking at over here, right? And this is the two-sided test. We have to multiply it by 2, right? So this thing here. This is how you know it's a one-sided test, because if you look at the upper thing here and you scan it over here, you'll see that it compares to this. So what you only really do, this is actually only a one-sided test. You need to multiply by 2 to get a two-sided test, right? So, but this means that instead of having to do this tidyverse pipeline here, you could have done the same thing with his built-in function in R, what's next in DevTools. So this is the context of your assignment that's coming up, right? So I will post this afternoon, and then you can kind of, if you need to rewatch and stuff, and I'll post our code on GitHub now. And if you need to look at it again for demonstration, you can feel free to do that. Other than that, I guess that's it for this week. Have a good week, guys.